Hello, this is Dr. Benjamin Norris from the Chemistry Department at Frostburg State University. Today we're going to talk about NMR spectroscopy, focusing on interpretation of hydrogen NMR spectroscopy. This is an sample NMR spectrum of the molecule ethanol. As I mentioned at the end of the video on how NMR spectroscopy works, an NMR spectrum contains multiple pieces of information that can be used to help us understand the structure of a molecule. The horizontal scale at the bottom of the spectrum is called the chemical shift scale, and its units are in parts per million, and they denote the difference in chemical shift or the difference in the resonance energy required or the radio frequency required to spin flip a proton in a certain magnetic field. The chemical shift represents the difference in that required for the proton in the molecule versus that of the internal standard. And it's ordered from high numbers on the left to low numbers on the right, because what we're actually measuring is how much less energy is required to spin flip these protons than those of tetramethylsilane. The number of peaks tells us something about the number of different types of hydrogen atoms in the molecule. The shape of the peaks tells us something about the number of neighboring hydrogen atoms, and the peaks themselves can be integrated to tell us something about the number of hydrogen atoms representing each peak. We'll talk about all of those each in their turn, working towards understanding how a structure of a molecule correlates with its NMR spectrum. In this slide, I just want to summarize the things I just told you, that we can get four main pieces of information from an NMR spectrum. The number of peaks. The number of peaks tells us the number of different types of hydrogen atoms in the molecule. The integration numbers tell us the number of each type of hydrogen atom responsible for each peak. The chemical shift tells us the chemical environment of hydrogen atoms in the molecule. And the splitting pattern, with that shape of those peaks, tells us the number of neighbors each hydrogen atom has. There's a little bit more to be said about the number of peaks and the splitting pattern than will be covered in this video. It will be covered in an upcoming video on complex splitting. In order to help us figure out how many peaks there are, we need to figure out something about chemical shift equivalence, usually shortened to just chemical equivalence. All hydrogen atoms within the molecule that have the same chemical shift will show up as a single peak. So if we can figure out which hydrogen atoms are all going to have the same chemical shift and which ones will have different chemical shifts, we can figure out how many peaks there are going to be. And by same chemical shift, we don't just mean that they're going to be really, really, really similar. They need to be perfectly the same. Because if they're not perfectly the same, then quantum mechanical weirdness will make them appear quite different. How do we know, then, how many types of hydrogen atoms are going to be in a molecule? I skipped a slide, sorry. Usually we can make some determinations based on symmetry of the molecule. For example, the hydrogen atoms attached to the same carbon atom are usually chemically equivalent. As I mentioned, there are some complex cases that will be covered in an upcoming video on complex NMR peaks. But for the most part, hydrogen atoms on the same carbon atom are usually chemically equivalent. Hydrogen atoms that are related by symmetry are also usually chemically equivalent. There is also a test that you can do. When in doubt, replace two different hydrogen atoms with a chlorine atom. If you generate molecules that have the same name, then they are chemically equivalent hydrogens. If the two molecules that you generate when you substitute out with the chlorine atoms are enantiomers each of other, the hydrogen atoms are still chemically equivalent. The chlorine test will be covered in more detail in that complex peaks, because it's a little bit more relevant to trying to figure out why you might have, say, more peaks than you would expect based on the structure of a molecule. Here are some example compounds that when we can use our understanding of the symmetry of a molecule to predict the number of peaks you might see in the hydrogen NMR spectra of these two compounds. For example, in the structure of propane in the upper left, there are two different types of hydrogens. The two methyl groups, one at each end of the molecule, are related to each other by symmetry. The structure of propane has a line of symmetry that can be drawn down through the middle carbon. Each of the three hydrogens in each methyl group are equivalent to each other, and the methyl groups themselves are chemically equivalent because they are related by symmetry. If you rotate the molecule around an axis or flip it in a mirror plane, the two methyl groups are interchangeable. Generally, any two hydrogens or group of hydrogen atoms that can be interchanged by a symmetry operation are going to probably be chemically equivalent, whether you flip the molecule around an axis or whether you reflect it in a mirror plane. This is why enantiomeric hydrogens, while maybe not related by rotational symmetry, they're still mirror images of each other, and they'd happen to be chemically equivalent. In ethanol, we have three different groups of chemically equivalent hydrogens. The three hydrogen atoms that are on the methyl carbon, the two hydrogen atoms on the methylene, the CH2 carbon in the middle of the structure, and the hydrogen atom on the oxygen. Cyclopentanol in the lower left has four different types of chemically equivalent hydrogen atoms. The OH, the hydrogen attached to the tertiary carbon there where the OH is attached, the two CH2 groups in the ring that are one carbon atom away from the alcohol, and then the two CH2 groups in the ring that are two carbon atoms away in the alcohol. And you can see here that there's another example of hydrogen atoms related by symmetry. This molecule has a plane of symmetry that goes through it, and what's on the left side is a mirror image of what's on the right. So even though the hydrogen atoms highlighted in blue are not attached to the same carbon, they are related by symmetry. And we're going to see that again in the structure of 4-methoxytoluene, which is the compound on the lower right. Again, this molecule has four types of carbon atoms. The methyl group attached to the oxygen on the left side of the molecule, the two hydrogen atoms in the ring highlighted in red, the two hydrogen atoms in the ring highlighted in blue, and the methyl group highlighted in purple, lilac, whatever that color is. Again, those hydrogen atoms across the ring from each other are related by symmetry and are chemically equivalent. You might trick yourself into thinking that all four hydrogen atoms on the aromatic ring are chemically equivalent, or that both hydrogen atoms on the same side of the ring are chemically equivalent. But some of those hydrogen atoms are closer to the ether, and some of them are farther away from the ether functional group. They would not have the same chemical shift because they're in different chemical environments. So let's go back and look at the NMR spectrum of ethanol. Now here's the structure of ethanol with the three different types of chemical shift equivalent hydrogens highlighted. In this case, because we have the integration numbers on the spectrum and the structure of ethanol is pretty simple, we can probably match up the peaks based on just counting the hydrogens responsible for each of the peaks, but we'll get to that in a minute. You can see that there are three different types of chemical shift equivalent hydrogen atoms in the structure of ethanol, and there are three different peaks in its NMR spectrum. We'll come back to the chemical shift thing in a minute. We'll come back to the chemical shift thing right now. So, as I mentioned in the previous video about how NMR spectroscopy works, the chemical shift is related to the radio frequency absorbed by resonating protons in a sample. And the difference between the sample and the standard, which is usually represented by the lowercase Greek letter delta, is called the chemical shift. And it's represented in parts per million to generate a chemical shift that's independent of the strength of the applied external field. Because it turns out the bigger the field, the larger the difference in chemical shift is going to be, the larger the absolute magnitude. But that difference is proportional to the size of the chemical shift, or is proportional to the size of the external field. So if we do some math, we can generate a chemical shift that is independent of the instrument that the data is being collected on, which would be good. What affects that chemical shift? Right? The chemical shift is dependent upon the magnetic field that is being felt by an individual proton. As I mentioned again in a previous video, the bigger the field felt by the proton, the larger the energy difference between the two spin states, and the higher radio frequency energy required to flip them. So now we're no longer talking about the applied external field. We're talking about something called the local magnetic field. And the value of B net, the local magnetic field, is changed by the magnetic fields of electrons in the molecule. Let's see how this works. If you remember that that charged particles that are moving generate electric field or generate magnetic fields, you would probably be suspicious that an electron orbiting around a nucleus, and of course electrons don't orbit the way around the nucleus the way planets orbit around the sun, but they do have some quantum mechanical property that's mathematically equivalent. Electrons, as they orbit around the nucleus, generate their own magnetic fields. And because the sign of the electron is opposite of the side of the proton, the local magnetic field generated by the electron is oriented in the opposite direction from the magnetic field generated by the proton. This local magnetic field generated by electrons shields the proton from the strength of the external magnetic field. Because B local is pointing in an opposite direction, it partially cancels out the external magnetic field. Protons with high B local, those are high field protons, feel a smaller B net or smaller net magnetic field and have a smaller chemical shift. Protons that have larger B nets, by having smaller B locals, in other words less shielding, have higher chemical shifts. And so you can divide the chemical shift range into two sort of areas. On the left, with the high chemical shift, you have protons that are experiencing low B local, so very little shielding from electrons. High B net, because they feel a lot of the applied external magnetic field, they have high chemical shifts. And these are sometimes called low field or down field protons. And these two words are in reference to the B local that they are feeling. But the more proper term for these protons are deshielded. These are protons that have low shielding. Okay. The other end of the NMR spectrum with low chemical shifts, these protons feel a high B local. There's a lot of electron density shielding these protons, so they feel a low B net. They are sometimes called high field or upfield protons because they feel high local magnetic fields from their electrons, but the most appropriate word to call these things are shielded. Though it's equally appropriate to use low chemical shift and high chemical shift, those two words are unambiguous as well. It's just a little bit confusing when low chemical shift is correlates to upfield and high chemical shift correlates to downfield. The internal standard used for nuclear magnetic resonance spectroscopy is called tetramethylsilane. It's an organic molecule that has 4 methyl groups off of a silicon atom. And this is the internal standard used for hydrogen NMR and also for carbon NMR spectroscopy, and we'll get to that in a later video. The low electronegativity of the silicon atom ensures that the protons feel a very large amount of shielding, both from the large amount of electrons on the silicon atom itself and feel the full effect of the electrons in the carbon-hydrogen bonds. The chemical shift of tetramethylsilane, or TMS, is assigned to be 0, and all chemical shifts are then assigned relative to TMS. if you go on and study further in chemistry, you might encounter a small number of compounds that have negative chemical shifts. But in organic chemistry, for the time being, we're only going to encounter compounds that have positive chemical shifts. The value of B local, the electronic field generated by the electrons in a molecule, can be impacted by electronegativity. As you know, electronegative atoms withdraw electron density through induction. So electronegative atoms can pull some of that electron density away from the hydrogen atoms, deshielding them a little bit. And so here are some examples based on substituting hydrogen atoms in methane for the different halogens. And as you go down this table, you go from no halogens to 3 halogens. The row for 4 halogens is not shown because those molecules, while they exist, don't have any hydrogen atoms in them, and so they wouldn't have hydrogen chemical shifts. And as you go from left to right, you go from iodine to bromine to chlorine to fluorine, which is increasing chemical shift. And you can see as you add halogen atoms to the molecule, the chemical shift of the hydrogen atoms that remain increases. So methane has a chemical shift of 0.23 parts per million, not a whole lot different from tetramethylsilane, but once you put an iodine atom on there, it increases to 2.17 parts per million. The second iodine takes it to 3.87, and the third iodine to 4.90. You can see a similar pattern for adding bromines, chlorines, and fluorines. As you increase the number of halogen atoms, the chemical shift increases. This table also highlights an important rule about chemical shift. In the presence of multiple things that deshield your protons or increase the chemical shift, those effects are additive. So one iodine atom deshields a little bit, 2 iodine atoms deshields more, 3 deshields even more. So it would be relatively unhelpful if we couldn't tell the difference in chemical shift change from having 1 chlorine atom or having 3 chlorine atoms attached to the same carbon atom. And you can see that the increases in chemical shift as you add halogen atoms also get bigger, depending on whether you have chlorines, bromines, fluorines, with fluorine being the most electronegative. There is another phenomenon that can deshield your protons, not just electronegative atoms. We talked a little bit about hydrogen, or about electrons shielding hydrogen atoms, but those are the electrons that are wrapped up in the bonds that those hydrogen atoms are participating in. Pi electrons, and there's no pi bond that involves a hydrogen atom directly, pi electrons also generate magnetic fields, but their B local is in the same direction as B0, at least at the hydrogen atoms. So here is a picture of ethene, one of the simplest alkenes, showing the magnetic field generated by the pi electrons in the carbon-carbon pi bond. In the middle of the pi bond, the local magnetic field of the electrons is pointing in the opposite direction of the applied magnetic field, which is similar to what we saw earlier, but the hydrogen atoms aren't there in the center. They're on the outside, and if you follow the circular arrows around to where the hydrogen atoms are, the orientation of that magnetic field is now pointing upwards in this picture, which is in the same direction as B0, the external field. So pi bonds have a tendency to increase the net field felt by hydrogen atoms, because the B local felt there is in the same direction. So pi bonds deshield nearby hydrogen atoms, and the biggest effect is felt when there is an aromatic ring in the molecule, because in an aromatic ring not only are there pi bonds, but there are pi electrons in pi bonds oriented in a circular pattern that can actually generate a current. So not only are those electrons moving in respect to their individual atoms, electrons in an aromatic ring are actually moving around the entire molecule. this particular aromaticity phenomenon will come back in the second semester of organic chemistry. But for right now, these moving electrons generate a current that generates an even more powerful magnetic field than other pi electrons, and increases the magnetic field felt by hydrogen atoms attached to aromatic rings to an even larger degree. Here are some example chemical shifts for hydrogen atoms in a number of different situations. Some reference chemical shifts are given at the top of the two columns. So the chemical shifts of the 12 hydrogens in cyclohexane all have the same chemical shift. They're all related by symmetry. That's one peak at 1.43 parts per million. But as soon as you put a double bond in the ring, not only do you now have multiple different types of hydrogen that are not chemically equivalent, you also generate some hydrogen atoms that have much higher chemical shifts. So the two hydrogen atoms attached to the alkene carbons have chemical shifts at 5.66 parts per million. And the presence of that alkene also increases the chemical shift of the allylic hydrogens one spot away to 1.99 parts per million, and it even increases the chemical shift of the other hydrogen atoms in the molecule even farther away from the alkene, to just a little bit though, to 1.61 parts per million. At the bottom of the left column is cyclohexanone, which contains not just a pi bond, but a pi bond to oxygen. So the electronegativity of the oxygen atom also plays a role in increasing the chemical shift. Because there are no hydrogen atoms directly attached to the carbon in that pi bond, the chemical shift increase, or there's no extremely large chemical shift increase, but the neighboring hydrogen atoms, those hydrogen atoms one spot away, still have a pretty large chemical shift at 2.35 parts per million. And then the other 6 hydrogen atoms around the ring have chemical shifts that range between 1.55 and 2.07 parts per million. So the effects of both electronegativity and pi bond deshielding can propagate a pretty far distance in a molecule. Benzene, on the upper right, has a chemical shift of 7.34 parts per million. So you can see a large difference even between the alkene hydrogens in the second structure at 5.66 and aromatic ring hydrogens at 7.34. If we put a methyl group on the aromatic ring, the hydrogens on that methyl group are deshielded down to 2.34, where they would have originally been closer to the 1.43 of cyclohexane. And then lastly, the structure of benzaldehyde has a carbon-oxygen double bond again. Because it's an aldehyde, we actually see a hydrogen atom directly bonded to a carbon sharing a double bond to oxygen. And the chemical shift of the aldehyde hydrogen is pretty large. It's up at 10.02 parts per million. So it's shifted to a higher chemical shift. It's deshielded both by being attached to a carbon shared with a pi bond and being attached to a carbon that's attached to an electronegative atom. And the effects of the aldehyde functional group also deshield a little bit the other hydrogen atoms in the aromatic ring. The nearby hydrogen atoms close to the aldehyde function group are at 7.87 parts per million, and the rest of the hydrogen atoms are still deshielded just a little bit from the hydrogen atoms in benzene. There's one last thing to say about chemical shifts, and that's the chemical shift of hydrogen bonding functional groups. The chemical shifts of hydrogen bonding functional groups, like alcohols and amines, are dependent on the solvent. The reason for that is that these are polar functional groups, and as the solvent gets more polar, these functional groups can interact with the solvent. And the more interaction they have with the solvent, the higher the chemical shift gets. Additionally, these polar functional groups can hydrogen bond with some solvents, and the more hydrogen bonding that occurs with the solvent, the broader and flatter the peak gets, until it might disappear altogether. And so you can see that in deuterated chloroform and dimethyl sulfoxide and deuterated water, the methyl group in methanol has a pretty constant chemical shift. It changes a little bit because the solvent polarity changes the overall electron density of the whole system, but the OH group has a chemical shift that varies from 1.09 parts per million in chloroform to 4.01 parts per million in DMSO to not being visible in deuterated water because of hydrogen bond mediated proton exchange. This slide shows a table highlighting the common chemical shifts for a number of common hydrogen atoms and in certain kinds of common situations. There's a lot of commons. This is a table of characteristic chemical shifts. And you'll notice that some of them are given as absolute numbers. So a methyl group has a chemical shift around 0.9, as long as that methyl group isn't doing anything more interesting. Likewise, a CH2 in the middle of a long alkyl chain is at 1.3, and a CH in the middle of an all alkyl stuff is 1.5. An allyl hydrogen is usually around 1.7. Hydrogens that are neighboring to carbonyl groups in the 2 to 2.7 range. Hydrogens that are attached to alkynes, 2 to 3, and you can go on down and see the effects of different types of groups on the chemical shift. As I mentioned, some of these are given as ranges, especially the more polar functional groups, because the solvent matters, the structure of the rest of the molecule can matter a little bit. And as a reminder, things that affect chemical shift are additive. So if you have a methyl group, that's a bad example. If you have a methylene, a CH2, that is allyl, so it's bumped up to around 1.7, but also is attached to an oxygen atom, you can expect that chemical shift to be higher than 1.7 because of the oxygen atom, but also higher than 4, which is the maximum for carbon-oxygen, because of the nearby pi bond. So these things all can add up. Some of the ranges you'll see are quite large. For example, the range on the alcohol, the amine, the phenol, which is the AROH, that's an alcohol attached to an aromatic ring. These are quite large because they're hydrogen bonding functional group. The aromatic ring region is also quite large. It can range from 6 to 9 parts per million, but most of them are between 7 and 8. And then it's nice that aldehydes are about the only thing that happen between 9 and 10, and carboxylic acids are about the only thing that happen between 10 and 13 parts per million. So here's our NMR spectrum of ethanol, and while I mentioned earlier that we can probably assign which peaks go with which hydrogen atoms in the structure based on the fact that the 3 peaks have 3 different integration numbers and we can count up the colored hydrogen atoms. We can also now better assign the peaks based on our understanding of chemical shift. The 3 hydrogen atoms in the methyl group shaded blue correspond to the peak with the lowest chemical shift. And so you can see that chemical shift is around 1.3 parts per million. And again, that oxygen atom, even though it's not directly attached to the methyl group, has dragged the chemical shift up just a little bit from the 0.9 that most methyl groups have. The CH2 in the middle of the molecule corresponds to the highest chemical shift peak, around 3.7 parts per million. And it has that high chemical shift because those hydrogens are bonded to a carbon atom that's bonded to an oxygen atom. And then the OH group has a chemical shift of around 2.6 in this case, and you can see that peak looks, the parts of the peak, first of all, there's only one of them there, it's not split into weird things. But while the splits in the other peaks are sharp lines, the OH peak looks a little broader. And that tells us something that we've got some hydrogen bonding going on. If you remember in IR spectroscopy, the peaks of hydrogen bonding things are broad because of hydrogen bonding. Same thing goes on in NMR spectroscopy. Now we're going to get to the issue of why some of these peaks don't look like single things. They look like 2 and 3 in complicated patterns. The phenomenon that creates that is called spin-spin splitting. It's a quantum mechanical funniness that generates or that causes peaks in NMR spectrum to split into multiple little sub-peaks. and it's created by the spin states of neighboring protons. So you have your protons that you're examining, but there are other nearby protons in the molecule, and they have their own spin states. And sometimes those spin states are aligned, and sometimes they're opposed. And if they're aligned, they increase B net just a little bit, and if they're opposed, they decrease B net just a little bit, and it perturbs the chemical shift of the protons you may be examining up or down just a little bit. And then depending on the number of hydrogen atoms that are neighboring, you can generate a predictable pattern of up and down. So now we're going to talk about how those splitting patterns can be generated. We're going to use ethanol again, and I've condensed down the structure so that it can fit on the page. On each type of hydrogen atom in the structure of ethanol, I've indicated the number of neighbors that that hydrogen atom has. So I've indicated that the hydrogen atom on the oxygen atom has no neighbors. It appears as a singlet, and I'll show you how that comes about in a minute. The hydrogen atoms on the CH2 group have 3 neighbors. Those are the hydrogen atoms that are on the neighboring methyl group. The hydrogen atoms in the methyl group have 2 neighbors. Those are the hydrogen atoms on the neighboring CH2. Generally, in trying to figure out which hydrogen atoms are neighbors, we are looking at hydrogen atoms on the next carbon atom over. The neighboring thing and splitting tends to get interrupted by heteroatoms, oxygens, nitrogens, and so on. And so even though this hydrogen atom is attached to an oxygen, which is attached to the carbon, which has these hydrogen atoms on it, the neighbor thing doesn't tend to happen across oxygen atoms or nitrogen atoms. And so OHs and NH2s and NHs don't often get split. Another reason is that you don't see splitting there is because of the hydrogen bonding broadening the peak out. So the hydrogen atom has no neighbors. That means there's no perturbation to the chemical shifts, and there is no change, so it shows up as a singlet, one peak. Right. The CH2 has 3 neighbors, and those 3 neighbors split that peak into a quartet, meaning it has 4 different substates that it can have, and we'll see how that comes about. Okay. Those 3 neighbors can have spins that are aligned in 8 possible ways. They can all be aligned with the external magnetic field. They can be set up so that 2 of them are aligned and 1 of them is opposed, and there are 3 different ways that can happen. They can be oriented so that 2 of them are opposed and 1 of them are aligned, and there are 3 different ways that can be happened. And then there is one state where they are all opposed to the external magnetic field, and we can organize them into 4 groups based on the relative effect on B net. So the state where they're all aligned with the external magnetic field creates a high B net, or a slightly higher B net than the other states. And there's only one way that can happen. The state where there are 2 aligned and 1 opposed also generates a slightly higher B net because the 2 is greater than 1, so it doesn't quite cancel out, but not as high as all 3 aligned. And there are 3 of them. So I've stacked them on top of each other, and you'll see what this is doing in a minute. There are 3 ways that we can generate 2 opposed, 1 aligned. Now we have a slight excess of opposed, so this generates a slightly smaller B net, and then 3 opposed, which generates an even smaller B net. These 4 stacks of possible spin states of the neighbors actually mirrors the number and shapes of the peaks that this is split into. So 3 neighbors generates a splitting into 4 peaks that have relative heights of 1 to 3 to 3 to 1, and this is why. 2 neighbors generate 3 peaks that are arranged in a particular characteristic pattern as well. Those 2 neighbors, so the methyl group has 2 neighbors in the CH2 group. they can be aligned in 4 possible ways. One way in which both spins are aligned with the external magnetic field, 2 ways in which one of them is aligned and the other is opposed, and 1 way in which they're both opposed. We can organize these into 3 categories as well. One in which both are aligned, slightly higher B net. One in which one is aligned, 2 in which one is aligned and one is opposed, no change to B net because they cancel each other out, and one in which both are opposed, so slightly smaller B net. And this 1 to 2 to 1 pattern is also the same pattern for the way that a triplet, or a splitting by 2 neighbors, appears. In general, splitting follows what's called the n+1 rule, that if there are n number of neighbors, the peak is split into n+1 separate little peaks, and the pattern that they follow is relatively predictable. So if there are no neighbors, n+1 is 1, it's not split really. We see one peak, it's called a singlet. We sometimes abbreviate that as S for singlet, and the relative intensities of that one peak is 1, is one of them. One neighbor, 2 peaks, we call that a doublet, and those 2 things are even in height, a 1-to-1 ratio of how tall they are. 2 neighbors, 3 peaks, triplet, abbreviated as T, and they are 1 to 2 to 1 in height. 3 neighbors, 4 peaks, quartet, abbreviated Q, 1 to 3 to 1. 4 neighbors, 5 peaks, pentet, 1 to 4 to 6 to 4 to 1. You can have 5 neighbors, 6 neighbors, 7. You can have as many as 9 neighbors. There's a way that works out, which would generate a 10 split for a decade, and you could predict the pattern of those. It would be pretty obnoxious to go through all of the different spin states and predict out the pattern. It happens that this triangle that's being formed in the pattern column is actually a known phenomenon, or is a well-recognized pattern of numbers called Pascal's triangle. And so in order to find the number of neighbors generated or the number of peaks generated when you split into 10, and they're in the way that their intensities go, you go down to the 10th row of Pascal's triangle, and that's what it would be. If there are more than one kind of neighbors, sometimes we can end up with a multiplet, which we represent with the letter M. Complex splitting is covered in an upcoming video. Sometimes more than one kind of neighbor you can't tell because they're pretty similar, and sometimes weird things can happen. So let's go back to our NMR spectrum of ethanol and look at the splitting patterns. Okay. Here are, again, all of the peak assignments, and you can see that the blue line goes to the peak on the far right, and that peak is a triplet. Now be very careful not to confuse the splitting pattern and the integration number. It's tough, it's easiest to do in a case like this, where you have a triplet that integrates to 3. The big 3 underneath the peak is representing the number of hydrogen atoms. The triplet tells us that it has 2 neighbors. The splitting pattern is not created by the number of hydrogen atoms on that carbon. It is generated by the number of hydrogen atoms 1 position over. We see the peak for the OH is a singlet, and we see the peak for the CH2 is a quartet because it has 3 neighbors. Here are some common splitting patterns. Methyl groups that don't have any neighbors show up as singlets that integrate to 3. And in this slide, you see that the integration numbers have been placed at the top of the peaks. Depending on the software that is being used, the integration numbers can show up in a variety of places. Okay? But usually they'll be above or below the peaks. An ethyl group, a CH2CH3, like we saw in the spectrum of ethanol, and this is not the spectrum of ethanol, but it's similar, has 2 characteristic peaks that are related to each other. The methyl group, the CH3, is a triplet that integrates to 3, and the CH2 is a quartet that integrates to 2. So if you have an ethyl group, you have to have those 2 things, and they're related to each other. a triplet that integrates to 3, so 3 hydrogens that have 2 neighbors, and a quartet that integrates to 2 hydrogens that have 3 neighbors, makes an ethyl group. And this is the NMR spectrum of the molecule ethyl acetate with the chemical shifts of the different groups noted. An isopropyl group generates a characteristic splitting pattern so that the hydrogen atom in the middle of the isopropyl group has 6 neighbors. So it generates a septet that integrates to 1. And very frequently, you can't actually see all 7 peaks. So the septet in this spectrum is this little guy down here around 3 parts per million. I can see 5 of the 7 pretty clearly, but all 7 of them are there. And then the methyl groups each have only 1 neighbor, and so they show up as a doublet, 1 neighbor, that integrates to 6 hydrogens. And then another common splitting pattern is the parasubstituted aromatic ring. So that is an aromatic ring where there are 2 substituents, only 2 substituents, and they're on opposite sides of the ring. They generate it as a pair of doublets, each integrating to 2 hydrogen atoms. And here is the structure of this molecule, para-isopropyl anisole. So let's come back and summarize what we've talked about. An NMR spectrum contains 4 critical pieces of information, at least a hydrogen NMR spectrum. The number of peaks tell you about the number of different types of hydrogen atoms in the molecule. The integration number tells you about the number of each type of hydrogen atom. Chemical shift tells you about the chemical environment of those hydrogen atoms. And then the splitting pattern tells you about the number of nearest neighbors each hydrogen atom has. In the next video on NMR spectroscopy, we're going to talk about complex splitting and the things that can lead to peaks that don't look like clear singlets, doublets, triplets, quartets, etc. Thank you for watching.